Okay, so here is our next optimization example for Math 1560, Calculus 1 at U of L for fall 2017. So again, we're in section 4.3. We're looking at these max-min word problems. And this time, our word problem involves constructing a box. Okay, so here's our setup, right? You guys can read it as well as I can. We want to make a rectangular box, open top, meaning there's no lid, and we've got some specifications for the manufacturer, right? We've got a volume specified. It must hold 10 cubic meters. The length of the base must be twice the length of the width, and material for the base, so we've got some costs involved. And so what we want to do here, let's read this last line. Find the cost of the materials for the cheapest such container. So what are we trying to do? We're trying to minimize construction cost. Okay, so we got to come up with a function that describes the cost of building this box. And so the first thing we're going to do is we're going to draw ourselves a box. Okay. Never hurts to have a picture. There we go. Okay, so here's our box, and we have also a box has three sides, right? So we can label the sides. We've got a length, let's call that X. We've got a width Y. We've got a height Z. Okay, and so now we look at our constraints, and so we have three variables here, right? X, Y, Z. So we're going to need some constraints if we want to simplify the problem. Well, the first one here, here's our first constraint: volume of 10 cubic meters. Okay, so that first constraint says that the volume, so the volume of a box is just length times width times height, has to equal 10. And for the base, right, the length of the base must be twice the width, right? So what does that condition mean? This condition here means that y must be equal to 2x, okay? So I can combine those two constraints, put these together, and what do I get? I get that 2x squared z equals 10. All right, so that's going to come in handy for us in a bit. Now, what's next? Next, we want the costs, right? So we got to do a little bit of work here to get our costs. So what is the cost? Well, the cost is going to be the area of the base, okay, times the cost of the material for the base, right? So the area in square meters times the cost of 10, right? In dollars, we're not going to bother with the units. So that's the cost of manufacturing the base plus the area of the sides times the cost of building the sides, which is 6, right? So we've got the 10 for the base, 6 for the sides. All right, so we know what the area of the base is. So the area of the base is just x times y, right? But y is equal to 2x, so this is 2x squared. The area of the sides, well, there's a couple of sides, right? So this side, right, there's two sides like this, and this side has area, so the base is x, the height is z, area is x times z, and this side has area yz, which is 2 times x times z. Okay? And there are two of each. So the area of the sides is going to be 2xz plus 2 times 2x z. And altogether, that's how many? 2xz plus 4xz, so 6xz. So my cost, once I put in these weightings, the $10 per square meter for the base and $6 per square meter for the sides, I get 10 times 2x squared, so 20x squared, and then 6xz times 6, so 36xz. All right, so there's my cost function, which I want to minimize. But again, it's a function of two variables, right? X and Z. I've only put in one of the constraints. I've put in this constraint here, that y is equal to 2 times x, which allowed me to eliminate the y variable. But I still have z in there. So how do I get rid of z? I come over to the volume condition, right? The total volume needs to be 10. I can solve this for z. Z, if I divide by 2x squared, 10 over 2 is 5. So I get 5 over x squared. Okay. So this value is going to have to be plugged in down there. And so that's going to give me my cost as a function of x. So 20x squared plus 36 times 5, 36x times 5 over x squared. Okay, so let's simplify that on the next page, and then we're going to see if we can minimize. All right, so our cost function is, so cost as a function of x, it was 20x squared. 36 times 5 is 180. X over x squared gives me 1 over x. So let's just jump back to verify that, right? So 20x squared, that's this term. X over x squared, this part here, that simplifies to 1 over x. 36 times 5, that's going to be 180. Okay, so that's where that's coming from. And we could also ask again about, domain, right? Do we have a domain that we can work with here? Well, yes. I mean, x has to be bigger than 0, right? Bigger than or equal, but already we can see that we're going to have a 1 over x in the cost function, so we shouldn't let x go to 0. Is there any limit on how big x can get? Well, not really. If x is really, really, really big, I can choose y and z sufficiently small and still have a volume of 10. It's not going to be a very useful box, right? It's going to be really long and really skinny and really short. But in principle, I could do that. So again, my domain, in this case, is anywhere from 0 to infinity. But I can notice that the limit as x approaches 0 of c of x is infinite, and so is the limit as x approaches infinity. Okay? So choosing x near either end of our domain is going to make the cost really big. We want to minimize the cost, so we're looking for a critical number somewhere in the middle. Okay? So this tells me that I need a local minimum, right? And this does tell me that at least this question makes sense, right? So let's say one of those limits was 0. Well, then there would be no, I could make the cost as close to 0 as I wanted, and I wouldn't have a minimum, and this wouldn't be an interesting problem. And since I need a local minimum, well, that tells me that we need critical numbers. Okay, how do we get critical numbers? Take the derivative. So c prime is going to be 40x minus 180 over x squared. Okay. So multiply that 40x top and bottom by x squared. 40x cubed minus 180 over x squared. All right. Now, of course, again, we're not allowing x to be 0. We don't have to worry about the fact that the denominator could be 0 here because x isn't allowed to be 0. So the only way for c prime to be 0 is if 40x cubed minus 180 equals 0. So that means that x cubed is 180 over 40, which is 18 over 4, which is 9 over 2. Okay, so this time we get, well, we don't get a particularly nice critical number. Cube root of 9 over 2. So we could look for an approximation on that value, but if we were actually going to try to solve this problem, practically, we would want to get an approximate value here so that we could, roughly estimate what x should be and then get the remaining variables. Okay, so x should be the cube root of 9 over 2. We want to verify the minimum. And we could do first derivative test here. It's a little bit awkward with the function that we have. We could go to the second derivative. So c double prime is going to be 40 plus 360 over x cubed when we take the derivative. And that's definitely bigger than 0 for x bigger than 0. And that tells me, using the second derivative test, that I do have a local minimum. Okay, so we found the minimizing value, so we know that x equals the cube root of 9 over 2. All right, now we go back, we got to reread the question. What were we trying to find? Were we trying to find x? Let's see. Find the cost of the materials. So the question actually wants to know the cost of materials. Now that we've got x, we can go back to our cost function and we can calculate the cost of the materials. So c of the cube root of 9 over 2 is going to be 20 times 9 over 2 to the 2/3 plus, well, 180 over the cube root of 9 over 2. Right? And if we had a calculator handy, which I don't, we could plug our numbers in and we could get some rough estimate on what that cost is going to be for building this box. Okay, that's it for this example.